Hi, I'm Orit and I'm a solution architect at AWS. Thank you for joining the multi-region deployment session. The reason I chose to talk about this topic is that in many cases when I talk to customers, I feel that they tend to rush into multi-region deployment. Multi-region deployment sounds good, it sounds global, but actually it is complex and not always needed. I'd like to make sure that when you decide to go with multi-region deployment, you'll do it for the right reasons. And when you do it, you'll avoid unnecessary complexity. We would like to keep things simple. So during this session, I'm going to review multi-region deployment motivations and challenges that arise. We'll go through mitigations or alternatives that might be relevant for certain use cases. We'll suggest different architecture approaches and reveal some tips and best practices on how to simplify the architecture. This is the first session out of 2-session series on multi-region deployment. The second part will focus on the disaster recovery use case. So let's start. Being a solution architect at AWS, I meet a lot of customers working for companies in various industry verticals. In many occasions, customers talk about growing their businesses top of their mind. But what drives companies' growth? Global expansion, increasing services consumptions through markets around the globe. Also, good customer experience. Good customer experience increases the engagement with the application and adoption of services. But what are the implications of addressing global markets? Does this necessarily mean multi-region deployment? And the answer is no. When I refer to multi-region deployment, I refer to the use case in which an application is deployed into multiple regions. So, to go multi-region or not to go multi-region? That's a question I tend to get a lot from customers. So let's start with why shouldn't you go with multi-region deployment? What are the caveats of multi-region deployment? Complexity. Deploying an application across multiple regions is complex. You'll have to extend the infrastructure across multiple regions in a secure way. You'll have to manage connectivity between those regions. You have to have global monitoring in place. Decide how you're going to do software rollouts to all those regions. It is known that complex systems are hard to maintain and prone to failure. In terms of cost, multi-region deployment might incur additional cost due to inter-region data transfer and non-optimized resource utilization. For example, there might be systems that you'll have to double or even triple, such as monitoring system and security checks. Let's talk about data synchronization. When we build our applications in a single region over multiple availability zones, we build stateless services that rely on databases such as Amazon DynamoDB, Amazon Aurora, and many other databases to replicate data seamlessly across availability zones. This enables horizontal scale and high availability. We would like to maintain this approach across regions as well, but we are bounded to the inter-region latency. Latency across availability zone can vary between single-digit millisecond to several tens of milliseconds. But latency across regions can get up to several hundreds of milliseconds. Therefore, inter-region latency is significant and introduces challenges around replication lag, data consistency, and conflict resolution. Also, out-of-the-box support for inter-region data replication in many databases is still limited. So, having said that, why should we go with multi-region deployment? And we have 3 main reasons for that. First is disaster recovery or high availability, the ability to withstand a regional system failure and transition the load effectively to a different region. Second reason is about data residency. When we have legal or regulatory compliance that requires that data and services must be hosted in specific geographic regions. Third reason that we mentioned before is a good user experience or fast and smooth user experience when interacting with the application without the overhead of long networking hubs. But before we dive into each one of those use cases, let's set some context in place first. Let's assume we have software as a service multi-tenant application. Multi-tenancy is an architecture in which a single software instance serves multiple customers or tenants. Multi-tenancy is efficient because software development and maintenance costs are shared. Therefore, this is commonly used for applications deployed in the cloud, and we have many use cases for this: gaming application, advertising and marketing applications, messaging, media applications, financial applications, and there are many more. The reason I chose to focus on Saas multi-tenant application pattern is that this represents a more general case, and solutions that will be suitable for this use case might also be relevant or suitable for other use cases, such as single-tenant applications. Now, with this context in place, let's now examine how multi-region deployment will look like for each one of the use cases we identified, or motivations we identified. First reason for multi-region deployment we mentioned is a disaster recovery, or the ability to withstand a regional system failure and transition the load effectively to a different region. In this case, based on your disaster recovery strategy, whether it's cold, pilot light, or warm DR, we will go with multi-region active-passive deployment. In this case, we will have unidirectional data replication set from the active region to the passive region. And there are several challenges around this deployment. We have to decide how we are going to manage the data replication across regions. We have to make sure we know to do the failover. We have to test the failover so that when time comes, we will do it properly. This will be discussed in more details in multi-region deployment part 2, so stay tuned. Another reason we identified for multi-region deployment is data residency. When we have legal or regulatory compliance that requires that data and services must be hosted in specific geographic regions. And we have many use cases for this requirement as well. Applications in the health and medical domain, financial applications, and many others. In this use case, we will mirror the application deployment across the required regions, to the required regions. And each region will serve specific tenant based on the tenant geographic affiliation. Therefore, in this use case, we will not replicate tenants' data across those regions. Challenges that may come in this use case are, first, we'll have to decide, should we keep all the services local, or are there any specific services that we should still keep global, such as monitoring service and billing service? Another challenge is, how do we route users to the relevant region? One approach for routing users to the relevant region can be assigning different domain or subdomain per tenant, and then using Route 53 to route users to the correct region. But usually, applications have several APIs, right? And we wouldn't like to have separate subdomain per API per tenant, right? We would like to keep things simple. Therefore, what we can do is we can use this approach only for authenticating the users. And once a user is authenticated, we can embed the tenant's data within the application URL. Then we can use Lambda at Edge to perform more intelligent routing. I encourage you to read blog post mentioned at the bottom of this slide, written by Todd Goldin, that dives deeper into this use case. Now we are getting to the third reason for multi-region deployment: the low latency user experience, or the ability to enable fast and smooth user experience when interacting with the application without the overhead of long networking hops. And we have many use cases for this requirement as well. We have gaming applications, productivity tools, e-commerce website, ad serving, and many more. In this case, we would like each user to reach the closest region based on her geographic location at any time, meaning we would like to be able to serve any tenant from any region at any given time. Therefore, we will require bidirectional data replication across those regions. But how do we keep all regions in sync given the inter-region latency? And given the fact that a certain user can reach region A at one point in time and region B at the next point in time. But wait, before we dive into or finding a solution to the bidirectional inter-region data replication, let's check several alternatives first. Remember, we would like to keep things simple. Therefore, the first alternative I would like to suggest is leveraging Amazon CloudFront for dynamic content. We are used to think of CDN in the context of caching static content. But Amazon CloudFront, with more than 220 points of presence around the globe, connected to AWS regions over AWS Global Network, can be leveraged for dynamic content as well. And this has several advantages. First advantage is leveraging the optimized AWS Global Network for communicating from the edge to the region, instead of communication happening over the internet. Second advantage is the fact that CloudFront makes use of persistent connections to each origin for dynamic content. This means we reduce the overhead of connection creation. One more advantage, or even another important advantage, is the fact that TLS and TCP handshake is done at the edge, which is geographically closer to the end user. Therefore, TLS and TCP handshake latency can be reduced dramatically. I encourage you to check last year's reInvent session of Tinder's use case, who demonstrated TLS handshake latency reduction from 3-digit milliseconds to 2-digit milliseconds, which is pretty significant. Amazon CloudFront supports WebSocket and HTTP protocols. This can be relevant for applications such as gaming applications, productivity tools, e-commerce websites, and many more. For applications in which WebSockets and HTTP protocols are not suitable, such as voice-over IP applications, UDP-based games, and real-time video applications, we can leverage AWS Global Accelerator. AWS Global Accelerator routes traffic to optimal endpoints over AWS Global Network as well. This improves the application performance and availability for globally used applications. Also, AWS Global Accelerator provides 2 static IPs that can be associated with the accelerator, and you can bring your own IPs as well. In many cases, we don't necessarily need to have all the services closer to the end user, but rather there is certain computation that requires the low latency performance. And we have many examples, especially in the security domains, for fraud detection applications and protection. Actually, I know at least one customer who has this solution in production running right now. So for this use case, we can take the computation that requires low latency and run it using Lambda at edge. Lambda at Edge is an extension of AWS Lambda service, a serverless computation service that enables executing functions at AWS locations around the globe which are closer to the end user. But if none of these options are good enough, we are back to the active-active multi-region deployment, in which we would like each user to reach the closest region based on her geographic location at any time, meaning we would like to be able to serve any tenant from any region at any given time. So we are back to the challenge of how can we synchronize the data across the different regions given the inter-region latency. How can we implement the inter-region bidirectional data synchronization? My advice for you is choose the right tool. That's a good advice, right? But how do we choose the right tool? We choose the right tool based on the application characteristics. We should look at what is the shape of the data. Is it key value, relational, document? We should look at what are the access patterns of the application. Is it high throughput, low latency, heavy on reads, heavy on writes, heavy on both? What is the consistency model required? Do we really need full consistency, or eventual consistency can be good enough? And how should we manage conflicts of concurrent updates? Now let's look at some examples. First example is real-time decision-making applications. Applications such as fraud detection, online games, ad serving. In those use cases, the shape of the data is key value. The access pattern is high throughput, low latency, heavy on reads and heavy on writes. Eventual consistency is fine, and last write who wins as conflict resolution is acceptable. For this use case, I would like to suggest the following architecture. We'll have the application services deployed behind a load balancer, of course. In this case, I chose the application load balancer. For the application services orchestration, I chose Amazon Elastic Kubernetes Service, or EKS. Similarly, I could have chosen Amazon ECS, AWS Fargate, AWS Lambda, or even EC2 instances. For the database, I chose DynamoDB Global Tables. DynamoDB Global Tables fit the application characteristics we described. Amazon DynamoDB is a key value and document database that enables single-digit millisecond performance at any scale. Amazon DynamoDB Global Tables is a multi-region, multi-master database that enables fast local reads and writes for massive-scale global applications. So how does it work? Amazon DynamoDB Global Tables consists of several replica tables, one per each AWS region, one in each AWS region, that DynamoDB treats as a single unit. Every replica table has the same table name and the same primary key schema. When application writes data to a replica table, DynamoDB propagates the write automatically to the other replica tables in the other AWS regions. And the replication happens usually within 1 second, in a typical latency of 1 second. So we actually have here a bidirectional inter-region data replication with DynamoDB Global Tables out of the box. This is simple. In addition, we will use AWS Global Accelerator to achieve two goals. The first goal is route users to the closest endpoint through AWS Global Network. The second goal is when we have an endpoint failure, AWS Global Accelerator will automatically route traffic to the next available closest endpoint within less than 30 seconds. Now let's look at another example. this time RDBMS-based applications. For example, project management applications, booking systems, e-commerce websites. In those use cases, the shape of the data is relational. The access pattern is heavy on reads, not heavy on writes, and we have medium sensitivity to latency. But full consistency is required, and conflicts are problematic. Therefore, for this use case, we can suggest similar architecture. This time, for the sake of diversity, I chose Amazon Elastic Container Service or ECS, but as I mentioned before, we can use Amazon EKS or AWS Fargate or AWS Lambda or even EC2 instances. But for the database, instead of Amazon DynamoDB Global Tables, we'll use Amazon Aurora Global Database. An Aurora Global Database consists of a primary AWS region in which the data is maintained and up to 5 read-only secondary AWS regions. Amazon Aurora replicates data to the secondary read-only replicas within typical latency of under 1 second. This means that an application can have local reads, but writes should be issued to the primary database in the primary AWS region. But we would like to keep things simple, right? So, with read replica write forwarding feature, the application can submit the writes to the local read-only cluster. This can simplify the application deployment. The application won't have to create and maintain connection to the primary database instance in the primary region. The application won't have to separate between reads and writes. And read after write consistency can be set at the session level. Read replica write forwarding supports 3 consistency modes for read after write consistency: session consistency, global consistency, and eventual consistency. And the consistency mode can be set as a parameter in the database session. Okay, summing up. For me, few lines of code are better than a few bullets in a presentation. So, if you're interested in global expansion, you should check your requirement first. If your requirement is about disaster recovery, the ability to withstand regional system failure and transition the load effectively to a different region, you should go with multi-region active-passive deployment. If your requirement is about data residency, the data and services must be hosted in specific geographic regions, you should go with multi-region isolated mirror deployment. And if you'd like to improve user experience and reduce the latency between the application services and the end user, you should first check if leveraging AWS Edge services gives you good enough improvement. And if not, you should go with multi-region active-active deployment. Of course, this function is a bit simplified. Sometimes it will be required to have both data residency and disaster recovery, and then you'll have to mix and match. Wrapping up, if there are 2 tips I'd like you to take from this presentation to make things simple, it would be leverage AWS Edge services as much as you can. Amazon CloudFront, AWS Global Accelerator, and Lambda at Edge. Also, do not reinvent the wheel. Use technologies with built-in inter-region data application, such as Amazon DynamoDB Global Tables and Amazon Aurora Global Database. Here you can find the references I mentioned during the session. And in this slide, you can find additional architecture resources. I'd like you to thank you for joining the session, and I'll appreciate it if you can complete the session survey and give us some feedback. Thank you.